Hello and welcome to this lesson for Module 6 of Particle and Medical Physics for OCR A-Level Physics, looking at the concept of electrical work done in the topic of electrical fields. So if we've been successful and we've learnt in today's lesson, we should be able to sketch and interpret graphs of V against R for positive and negative point charges, describe how the potential difference can be deduced from a graph, and consider how the potential gradient of a field is linked to the electrical field strength. Now in our previous lesson we've considered the following planes of equipotential in an electrical field. Now an equipotential line is a line or surface along which the electrical potential is the same, much like a contour line for a height on a map. Now equipotential lines are very useful when interpreting the electrical field strength near charged conductors. However, we can also consider the planes of equipotential to be like blocks. So here is another way of visualizing electrical potential. Now this is a representation of how the electrical potential varies in an electrical field. So we can consider a representation of how the energy stored per coulomb varies in an electric field. So this produces what we call a potential gradient in the electrical field. Now our potential gradient can be thought of as the change in electrical potential with respect to distance. So we can think that the closer the planes of equipotential in the field, the greater the potential gradient in the electrical field. Now charged objects can travel down the potential gradient, but work must be done to achieve this. So here the electrical field is doing the work to move the charge. So we can say the electrical field is attracting the charge. So we know the electrical field is doing the work moving the charge, so we consider the work done to be negative. So when there's attraction between the charges, we say our work done is negative. Now electrical fields can also produce no potential gradient as well. So if a charged object does move along a potential gradient with nothing, then no work must be done. This is a line or surface of equipotential. Now, going down a potential gradient, work is done out of the system, while going up the potential gradient, work is done into the system. So in this case, we have a positive value for work done. This is when there's repulsion between the charges and we have a positive work. Now the steeper the potential gradient, the more work that must be done to that charged object. So a steep gradient means that a lot of work must be put into the system to move the charged object up the gradient. So it means that a steep gradient can have a lot of work being released from the system to move a charged object down the gradient. So the potential gradient at any position in an electrical field is the change of potential per unit change of distance in a given direction. If the field is non-uniform, the potential gradient varies according to the position and direction. The closer the equipotentials are, the greater the potential gradient is at right angles to the equipotentials. If the field is uniform, the lines of equipotential are equally spaced out, so our potential gradient is constant. Now we can graph this concept of potential gradient. So the gradient of this graph of V against R is called the potential gradient. So as we said before, the change of potential per unit change of distance in a given direction. So the closer the equipotentials are, the greater the potential gradient. So this means the graph will be the electrical potential against the distance from the charged object producing the electrical field. So the steeper the line, the greater the potential gradient, the more work that must be done into or out of the system. So our gradient is the change in y over the change in x, or delta V over r. Now we can place this equation for potential into the following equation. We know the gradient is delta V over r, where V is q over 4 pi epsilon 0 r. So we divide that by r. So therefore this tells us that gradient equals q over 4 pi epsilon 0 r squared. So this means that the potential gradient is the same quantity as the electrical field strength. So potential gradient is the electrical field strength. The gradient of a V against R graph is the electrical field strength. So we can consider the potential gradient as the magnitude of the electrical field strength. Now this is because it doesn't show the direction of the field. So as we said before, we can graph the potential gradient for a uniform field. The gradient of this graph is our potential gradient. Here, the equipotentials are equally spaced out, giving a straight line. So the electrical field strength doesn't change, as such the gradient doesn't change. So as mentioned, the electrical field strength is equal to the potential gradient produced. So here, our equipotentials are equally spaced out, the electrical field strength doesn't change, our gradient does not change. because the electrical field strength is equal to the potential gradient. So in a uniform field, the electrical field strength is constant, so the gradient is constant. You get a straight line. Now here we can see that the electrical potentials can change how spaced out they are as the field lines spread out, so our electrical field strength does change, indicating that gradient will be changed because the electrical field strength is equal to that potential gradient. So in a radial field, our electrical field strength is decreasing with respect to distance, so the gradient is decreasing, you get a curved line. So here is a comparison between the two graphs illustrating the potential gradients produced. You can quite clearly see the link between electrical field strength and the gradient of the line. Here, the gradient follows the trend for an inverse square law because E is equal to Q over 4 pi epsilon 0 r squared. Here, our gradient is constant for a uniform field as the electrical field strength doesn't change. Now from the previous graph we can also derive another key idea. Now do note that the gradient of the tangent to the graph will be the gradient or the electrical field strength of the field. So here V is changing with R for a positive charge as we define the field in terms of positive charges. V is initially positive and tends to 0 as R moves to infinity. Whilst here, V is changing with R for a negative charge. Again, now we're defining it in terms of positive charges, we must have a negative value for a negative charge. V is initially negative and tends to 0 as R moves to infinity. So if we consider the gradient of our graph here, gradient is delta V over R, which is the electrical field strength. We can rearrange this equation to make delta V the subject. So delta V is equal to E times by R. So this shows us that the area under the line of an E against R graph gives you the potential difference a charged object experiences, because the area is equal to the y-axis times by the x-axis. So if you're asked to estimate the potential difference on delta V from an E against R graph, you will have to work out the area under the graph by counting the number of squares or by splitting the areas up into trapeziums. This concept allows you to derive the electrical potential equation stated earlier in the course. It's the graphical derivation for the equation of electrical potential. We know E is equal to V over R, so V is equal to ER, so we know V is equal to Q over 4 pi epsilon 0 R squared times by R, so at that point we can say V is equal to Q over 4 pi epsilon 0 R. So you must be aware of the electrical properties from two electrical field graphs. So in our electrical potential against different distance graph, V against R, we can say our gradient is the electrical field strength. Whilst the electrical field strength against distance graph, ER, the area is the potential difference. So this can be summarized in the following table, that we can see that the force is equal to Q1 Q2 over 4 pi epsilon 0 R squared. The potential energy, which is the area under an F against R graph, is equal to Q1 Q2 over 4 pi epsilon 0 R. The field strength, which is also the potential gradient or the gradient of a VR graph, is equal to Q over 4 pi epsilon 0 R squared. Whilst finally our potential, which is Q over 4 pi epsilon 0 R, is our area under an ER graph. So thank you so much for watching this lesson on electrical work done, which is part of the electrical fields topic in Module 6 of OCR A-Level Physics, which is particles in medical physics. Thank you so much for listening to this video, and as always, have a lovely day.